Okay, so last time, just a quick overview of page 1. We started with Newton's second law and derived the impulse equation. Same variables, just we're giving it a different name in this different grouping. And so change in momentum, AKA impulse. And so we saw a couple equations for that. And then we used impulse and Newton's third law application to get our conservation of momentum, linear, because later we'll have angular. And then we got to the types of collisions. We said your ideal situation is going to be elastic, and that's at Newton's cradle or billiard balls. That really, those are the only 2 examples. And then these last 3 are really just considered inelastic. Okay, at the end of the day, there's only 2 types of collisions. Elastic, which if you check out our last column there, kinetic energy is conserved with elastic, but all 3 inelastic does not. That's your official distinction, okay? You'll find some like, generic physics websites that'll say, oh, it's if they bounce or don't bounce. That's not the AP definition, okay? They dig deeper. And so elastic, Newton's cradle that I did, that's not the right one. I ran out of paper. Follow along in OneNote for now. And so you have bounces in elastic, but the most important part is that no energy loss, okay? The kinetic energy is constant within the system, but you do get that bounce off. But you also have a bounce in partially inelastic. So this is like hitting a tennis ball, hitting a baseball, right? Kicking a football. You have a bounce off, but due to deformation and contact frictional forces, you lose some energy in the form of kinetic. And then if they stick together, it's completely or perfectly inelastic. That's the one that most people say, oh, that's inelastic. They forget about that intermediate definition one. And that one has the most energy loss, most contact, most loss. And the last one to fill out here, depending on what book you read, it doesn't really have an official name. Some textbooks just say, oh, explosion. But we don't always explode. It could be a kid jumping off a skateboard. And so in that case, I like to call it an anti or reverse collision, okay? And so whatever we call it, what makes it different than the others, they start separate, and end, no. They start together, sorry, and end separate. Hold on, OneNote's going crazy. And end separate. So like I said, that kid jumping off of a skateboard, and it doesn't have to be a kid, a person jumping off a skateboard is an example. And so they start as one, and then they separate, okay? The system is them together. And what's unique about this one, it doesn't have to be true, so I'm not going to put it in the table, but explosions or jumping off a skateboard, typically, 90% of the time-ish, you start at rest, okay? Before the explosion, before the jump. You have zero velocity, you have zero momentum, zero kinetic energy. After you jump off the skateboard, both objects are moving. Now you have momentum, now you have energy, okay? And so that one is weird. It doesn't feel like momentum should be conserved until you consider direction. If I push my podium forward, if I was on a skateboard, what would I be doing? If I push the cart forward, I would go backwards. So imagine I have a skateboard here, right? And so that backward is going to be important to momentum because don't forget, energy may be scalar, but momentum is a vector, okay? So direction matters. Any questions about the two types of collisions? There's two categories, elastic, inelastic, but we just broke down inelastic into three different styles, if you will. The big thing is that kinetic energy. In 98 days, when you see a problem on the AP exam with the word elastic, don't say to yourself, oh, that just means they bounce off. That's not the end of the story. The full story is kinetic energy and momentum are conserved. Okay, well, let's do some practice. So my goal today is 2 through 6. It's, page 6 has a level 3-ish, but most of these are, level 1, level 2 type of problems. So they hopefully go quicker. So page 2, as easy as it gets. The following forces are applied to the same object. So mass is not going to change, which provides a greater delta P. And I know that's capital. I blame word. It should be a lowercase p because we're not talking power. What's our new lowercase p? Momentum. And so a change in momentum. Rank the following scenarios. A, you have, again, pick an object, whatever it is, a box. You push it with 4 newtons for 1 second. What's your change in momentum? Are we going to use the M delta V version? Do we know the mass? Do we know the velocities? No. What's our other equation equal to change in momentum? Force times time. And so that force times time is that impulse. Change in momentum is impulse. So once you realize that, the math is easy. 4 times 1, 4 Newton seconds. B would be 6 Newton seconds. Those are constant forces. But what makes C a little trickier, it's not a constant force. I've got 1 Newton for 2 seconds, and then immediately following 2 newtons for 1 second. What do we do with that? Average, does that mean I use 1.5 newtons for 3 seconds? I know that we talked about average force, right? But if you were to look just at B and C graphing, force and time, this would be a constant force, right? This one would look a little different. I'd have 1 Newton for 2 seconds, and then I would have 2 newtons for 1 second. I don't want to do the average here. Graphically, how do we find impulse? Do you remember? Area, and so the area of, we'll break it up into 2 rectangles. Look at it as impulse part 1 and impulse part 2, and to get our final answer, we will add them, right? And so what do we get for object C? Impulse 1, impulse 2, we get 4 Newton seconds, okay? And the numbers were chosen because if you averaged 1 and 2, 1.5 times 3 seconds, you'd get not 4, right? So it'd be a difference. And so B is greater than A, equal to C. Good deal. The average force is when we had a non-constant force, which I know that overall we don't have a constant force there, but you'd have to do a time-weighted average. Ooh, I just said a curse word, right? Time-weighted average, if you did the 1.5. Okay, so staying away from that because nobody really likes that one. But you use the average force in that non-constant reference. Okay. Question 2, we've got a 50 kilogram object. Initially, we got 3 different initial velocities. At rest, so VI equals 0. Moving right at 10 meters per second, moving left at 10 meters per second. Does direction matter for impulse and momentum? Oh yes, it matters. Who's positive today? Right or left? Because ultimately it doesn't matter. What do y'all want? Right, so standard sign convention, we'll call right positive, left would be negative. And so I've got these three different initial velocities. Now we're going to exert a force of 20 newtons. We're going to exert a force of 20 newtons for 2 seconds on each of these scenarios. Rank the following. Delta P, again, you might say, oh, that's m delta v. Do we know the change in velocity? They only gave us the initial. To get change, you need final minus initial. Do we know final velocities? Should we assume 0? Did they say it comes to a stop or anything? No. And so plan A, not going to work. What else is equal to change in momentum? Force times time. And so that F delta T, net force, they only tell us 1. We'll assume there's only 1, times that time interval. This is the time that the force is exerted on the object. And so, do they differentiate the force and time on each scenario? No. And so we can assume that it's the same 20 newtons over the same 2 seconds. And so 20 times 2 gives us, it's a positive 40 newton seconds for which scenario? All of them. So our ranking would be ABC, all equal. Everybody good? So moral of the story, impulse is not a one snapshot in time. It's change, okay? It's a change in momentum. And then B, we need the final momentum, the absolute value. So don't misinterpret absolute value. We don't care, we do care about direction, just not at the end. Don't say, oh, this means I can ignore the left. No, we have to consider direction only till the very end, okay? And so what can we do? Well, change in momentum is equal to a final momentum minus initial momentum. Hold on. Come on, there we go. And so I'm going to solve this for final momentum. And so we get final momentum, add initial to the other side. And they don't give us the initial momentum. What could we plug in for initial momentum? Well, they gave us mass, they gave us initial velocity. Don't forget momentum is 1/2 mv squared? No. What's momentum? Mass times velocity. So that initial momentum is going to be mvi plus the impulse. Now they're all going to have the same impulse. And so let's do it for each. So the final momentum for situation A would be, well, 0 would be your initial momentum if you start at rest, plus 40. So it would have a final of 40. And Newton second, now I'm going to switch over to kilogram meters per second. Remember, these two are equivalent. You can use them interchangeably. What about B? Well, it would be mass, which they said was 50. Initial velocity was a positive 10 plus a positive 40 impulse. What's your final momentum for B? Y'all can talk to me, you know. It goes better and quicker if y'all talk to me. So positive 540 And then for C, the difference here, same mass, but now it's moving to the left. It's getting pushed to the right. What's going to happen to the momentum of an object if you're moving left but pushed to the right? You're not going to have a positive change, right? Or you'll have a positive change, but your speed is going to decrease because you have a decrease in your momentum. And so here it's negative 500 plus 40 or negative 460. So I can't ignore the direction completely, but now that I have my answers, absolute value, everybody, what would be our ranking? B is greater than, C is greater than A. Good deal? All right, number 3, given the following conditions. So concept, mass 1 is greater than mass 2. We don't know by how much, we just know the ranking of the mass. Force, the same force is going to be applied over the same amount of time. So if force and time are the same on each object, can we rank their change in momentums? We did it twice before. What's the first ranking here? If they have the same force for the same time, rank their change in momentum, aka impulse. What would we get? They're all equal. They're both equal, right? Or same, however you want to say it. And so again, they may have different mass, but they're given the same change in momentum. They're both given the same force in the same amount of time. They have the same impulse. But now rank their change in velocity. Now we don't know their initial velocity. That's okay. We don't know their final velocity. That's okay. Because we can say, well, I know change in momentum is mass times change in velocity. If they have the same change in momentum impulse, then the one with the smaller mass will receive what kind of change in velocity? Greater. And so rank the change in velocity. If M1 is greater than M2, who's going to get the greater change in velocity? 1 or 2? 2. It's got the smaller mass. So because M2 has a smaller mass, change in V2 is greater than change in V1. Good deal? And we couldn't take that one further, like rank their final velocities or momentums without knowing some initial information. Okay, let's do a little bit with numbers. So hopefully there's a calculator nearby. We'll have a little bit of calculations today, mainly concepts, but have a calculator ready. Let's talk baseball. We're going to hit the baseball. So the pitcher throws the ball towards the plate, home plate. The batter hits it, right? Initial velocity of the baseball is 8 meters per second. Final velocity is 20 meters per second. Wait a second, did they just give me velocities? 8 and 20? When the ball comes towards the batter, and then the batter hits it, it leaves a different direction. So technically they gave us speeds. Momentum cares about direction. Somebody's got to be negative. What do y'all want? Is the 20 or is the 8 positive? 20, you say, is positive. So it's coming in towards us at a negative 8 meters per second. And we're going to hit it and it's going to go out at positive 20. But we got to appreciate direction. Mass, 0.2 kilograms. And then they tell us the bat and the ball are in contact for 0.07 seconds. And remember, the delta T in impulse is not the time that it takes to go to the outfield. It's not a projectile time. It's the time that the force is being exerted between the objects, okay? And so it's that impact time. It's the hit time, kick time, launch time. A, what's delta P? So previously, we've done a lot of force times time. Is that going to work here? No, we don't know the force. What else is impulse and change in momentum equal to? M delta V, which we do know the mass of the ball, so we can find the impulse on the ball. I'm going to get technical here. And we can use the mass of the ball and the change in velocity of the ball, okay? And so 0.2 times final velocity 20 minus what? -8. Be careful on that one, because if you didn't consider direction, you would just have 20 minus 8 with a difference of 12. But we should actually get 20 minus a -8. Or if you chose the other direction as left, you'd have -20 minus 8. Okay? And so either way, this part should be 28 and multiplied by 0.2. What do we get here? Yeah, 28 divided by 5, so 5.6 sounds familiar. Unit. You got two options. Newton second is 1. Now, or kilogram meter per second. My norm is typically, and I'm going to add a positive there, if I use mass and velocity to get the answer, I use kilogram meter per second. If I use force and time, I use Newton second, but they're interchangeable, okay? Tomato, tomato there. Now I did put a positive, okay? Because up above, we said the ball was going to change in the positive direction, right? It was going to go in the positive direction. The force on the ball is in what we've defined as left positive. Good deal? What if B, I'm going to change B a little bit. What if B said J, well, first of all, what is that? Is that joules? What's J? It's impulse, okay? What is impulse equal to? Change in momentum. Didn't we already find that? And so it's going to be the same number, but I'm going to add something to it. What if it said J, or impulse, on the bat? They did not give us the mass of the bat or the velocities of the bat, but you don't need to. What's the impulse on the bat? Remember Newton's third law? When you take those equal and opposite forces and multiply by time, you can look at it as equal and opposite impulse during that hit. And so with that, the J on the bat would be the opposite. So not a positive 5.6, a negative 5.6. Newton second, same, right? Use them both. So just to reiterate that Newton's third law. And then we get to F average. Solve for that average force. So here's where you got to ask, okay? Previously, we talked about average force. Is that bat and ball interaction going to be a constant force? Or is it going to be a variable force? One that maximizes at full contact, but maybe it starts and ends with minimum contact, yes? So this is that non-constant type of situation. When the ball just barely touches the bat, minimum force. And then when it, have y'all ever seen slow motion of either a baseball, football, tennis ball getting hit? It actually contracts. It bends in, right? It smooshes. I'll try and find that video too, okay? And so at maximum force, you've got that maximum smush. And then it's going to uncontract, decontract. That's weird. Stretch back out, okay, as it leaves the bat. Now, there's no graph. We're just going to do a basic solve. Now that we know the impulse, now, and we know the time, how are we going to find the average force? Well, we divide both sides by time. And so F average would be that momentum change divided by time. And so if we look at, they don't say bat or ball, so it's just a sign change, right? I'll keep with the positive. We'll do the ball. Average force on the ball. And so 5.6 divided by 0.07. Work that out. Let me know what you get. Grab a calculator. I don't remember this number. No, he's working on non-physics, so he doesn't need a calculator.
That's physics.
I don't think so.
It's 80.
80, I hear. And so I got to rag on you when I can, right? And so the force on the ball is a positive 80. What if they said the force on the bat? Negative 80. What if they said, what's the maximum force? If you know the average force, assuming it's changing at a constant rate, triangle, right? How would we find the maximum force? Well, F average, this works just like our velocity did back in the fall. It'd be the minimum plus the maximum divided by 2. Minimum would 0 be here. And so how would we find the maximum? Multiply by 2 and get 160. Okay.
Wait, we was only asking for average.
I know, I just took it further. Final answer for the one asked was 80. That's your average. There's your average. Okay. But just to drive the point home, it's not a constant force when you hit a ball. Okay. All right, let's do the last one on that page. Still numbered. Oh, yeah, it's a continuation. What if the bat is going to break at 50? And we'll go on the assumption we don't want to break the bat. Okay. So it's going to, if I hit it with 80, break. Well, we don't want that. What would be the maximum speed that the ball can be hit, assuming that the time of contact is still the same? And so we just rearrange our m delta v equals that force times time. And so what are we solving for? Oh, break up our final minus initial. And so final minus initial. We would be solving for final. Now, they don't tell us anything different, so we can assume the initial velocity from the pitcher would be the same, right? And so final velocity would be the force times time. We can divide by mass and then add VI. Yeah? And so the new force, 50. Time is the same, 0.07. Mass, 0.2. Plus, what was the initial velocity again? -8. Careful there. And get me the new final velocity. What do we get? 11.5? I don't remember that one. 9.5. So 9.5, and it should have come out positive. Okay, we're still going to hit the ball away from the batter, which we said was going to be the positive direction. So hopefully you literally got a positive 9.5, yes? Okay. But if you didn't have -8, you would have got something very different. Okay, questions on, these are level 1 type of questions. Kind of plug and chug. You plug and chug a concept, you plug and chug a number, right? Well, let's go to page 3. And by the way, we're going to do 3 together. Later, y'all are going to do page 4. So pay attention here. What are we going to do? I don't know if you remember all the kinematic graphs. We walk the graphs. We dissect the graphs, okay? Graphs are more than just reading it. You got to kind of get into that story. That was the initial velocity of the ball. We had made it negative in the very beginning, and there was no indication it was changing. There you go. Okay, so let's walk the graph. Let's tell the story, because even though these questions are what they are, we got to be ready for any question, right? And so I'm going to use colors as best I can. Well, first of all, read the axis. What kind of graph is this? It's a force time graph. Now, the mistake I see students make, first question, when does it change direction? Oh, well, it's when it crosses the axis. That's only true if what axes do you have? Velocity. So if it's a velocity time graph, yeah, where does it cross? But this is not a velocity graph, but we do need to know something about velocity, right? And so knowing what you need to answer the question is important. And so we need when velocity equals 0. Well, one thing we do have to edit here, we need an initial velocity. And so I'm going to match the key. And so add this in, everybody. We'll make it easy on this one. We're going to start from rest. And later we'll need the mass. We'll say it's 4 kilograms. And so if we start at v equals 0, now that doesn't mean that's our answer. When do we return to 0? And so just to put information, I'm not reading the graph, I'm just adding information to it. So if we start from rest, what's happening in segment A? It is accelerating. It's accelerating the whole time. So can you be more specific? Okay, and how do you know it's a positive acceleration? Okay, so 2 ways to look at it. Y'all remember Newton's second law, right? What's Newton's second law? Right, and so what do we have plotted here? We'll pretend it's net force, right? There's no other forces given. And so it's a force. Well, mass has no direction. And so you can kind of interpret this as an acceleration graph. Different numbers, true story, because the mass is not 1, but the trend is the same as whatever you see on an acceleration graph. So you could look at it that way. Remember, a force is your push or pull. And so it's not telling us what we're doing, it's telling us who's pulling on us. So if I start at rest and the positive rope, if you will, pulls on us, we're going to do what? If I'm standing still and someone pushes me to, we'll say, the right, what am I going to do? I'm going to move what direction? I'm going to move to the positive direction. Okay. And am I going to move fast, slow? Am I going to slow? I can't slow down if I start at 0, right? So what's the velocity going to do? Speed up. Now I just did the old way of storytelling. What's the new way? Well, it's a force time graph. And so the area tells us what? What does the area tell us? What kind of momentum? Change in momentum, right? And change in momentum is m delta v. I'm going to have a positive change in velocity. Now, I haven't done the numbers yet, and I really don't want to yet, but the area should give us enough, and I gave you the mass. You should be able to find the velocity that you end with at 2. It's going to be what sign? Positive. Greater than 0 and larger than 0. Wait, did I just say the same thing? Sorry. It's going to be bigger than 0 and it's going to be positive. Okay. It's Virtual Friday for us, right? Okay, let's keep going. So by the way, do you change direction when it crosses the axis? 2 seconds is not the answer. Let's keep going. Now, what about segment B? Now who's pulling on us in segment B? The opposite direction. So we were going to the right. Now we're getting pulled to the left. What's your object going to do? Here's where we start to slow down. But what direction are we going? We are still going in the positive direction. And your confirmation of that, look at your area. I have a negative change in momentum, a negative change in velocity. And what's very nice about segment A and segment B's area? They're equal and opposite. And so here we have area symmetry. And we learned in the fall, it's been a while, but they're going to cancel out. So what's your final velocity at the end of 4 seconds? It's whatever it was when the symmetry began, right? And so at this point, V4 equals V0. And that means at 0 seconds. What did we start with? The initial velocity started with zero. So now we've returned to 0. We've come to a split second stop at 4 seconds. Do we guarantee turnaround? You might remember my drive-through example, right? You come to a stop to get your food in the drive-through, but hopefully you don't change direction. Okay, I don't want to be behind your car if that's the case. So how do we know if we change direction? Look at the future. What does the future tell us? 4 to 6. So we know we start at 4 seconds at a stop. We have a negative change in momentum, a negative change in velocity. What direction are we going now? Negative. So C is the negative direction. Can we answer question 1 yet? At what time does the object turn around? Change direction. 4. Okay, before 4, we were always going the positive direction. After 4 seconds, at least in that 4 to 6, we're going in the negative. And so it's at 4 seconds that we turn around. Good deal? Now I'm going to keep the story going. Okay, we'll need it later. Let's keep our story going. What about D? D still has negative area, not as much, but we still have a negative change in momentum, a negative change in V. So what's our object doing in D? Not yet. You're still, actually, we didn't say this in green. Let me go back to green. Are we speeding up, slowing down, constant speed in C? We have in C, we have a constant force, constant acceleration. So we would be speeding up in the negative direction. In D, purple, we still have a negative force. It's just not constant. So it's still pulling us to the left, just not as much. So let me ask again, what's the object doing in D? we're still speeding up, and I'm just going to add in a little bit, not as much as C, but we're still speeding up a little bit. What direction are we moving? Negative. We're still moving in the negative. It's got positive slope, but we're not looking at slope, right? Okay, it's decreasing to 0, but it's the force that's decreasing, not my velocity. And so you got to consider that area. I said negative direction. Okay. Do we turn around at 7 seconds? Cross the axis? Is that how we answer the question? No, that's just when the pull changes direction. And so what's happening in E? Now I'm getting pulled to the right. Look at your area here. I got a positive change in momentum, a positive change in velocity. So we were speeding up going to the left. Now somebody pulls us to the right. What's going to happen to this object? It's going to slow down. Is it enough to cancel all that speeding up that we did in C and D? Not the whole thing. So we're going to slow down a little bit. Hint, hint. What direction are we moving? Still negative. Just because there's a positive force doesn't mean you're moving to the positive direction, okay? Now, I hinted, you don't cancel the whole thing. E will cancel what? D. And so what that tells us is the velocity at 8 seconds will return to the velocity at the beginning of the symmetry, 6 seconds, okay? We don't know that number, but that symmetry returns you to that initial, the velocity before the symmetry. Good deal? Okay, questions on the story? Got some more questions here. Okay, next question. At what time did maximum speed, who cares about direction, occur? And so in A, we speed up, I would say a good amount, but then we slow down that same good amount. C, we speed up a rectangle amount, right? We speed up a little triangle, we slow down a little triangle. Where do we have the maximum speed? At 7 seconds, okay? If you even just eyeball it, the area of green and purple of C and D is bigger than the area of A. Our story said A, C and D were all speeding up, but C and D is the bigger speed up. And so at 7 seconds. And also the other thing to point out, how do you find max speed? Remember, it's before the slowdown. Now, before we do the next 2 questions, which are going to have us calculate, I just want to finish the concepts, get them out of the way. So skip down to E. Which line segments, A, B, C, D, E, show a positive acceleration? I've already hinted at this answer. Where do you have a positive acceleration? A and which one? E. Why A and E? Am I looking at slow? What are we looking at? Force is positive. So remember Newton's second law, F net equals ma. If you want a positive acceleration, you got to have a positive force. Final answer, A and E. Which line segments show, and that's a little misleading because none of them show, which line segments include positive velocity? And remember, the sign of the velocity tells you what? Direction you're moving. That's how we looked at it. So when are you going in the positive direction? A, B, and that's it, because everybody else was in the negative direction, right? So even though they have different sign forces, okay, A and B are when we said you were moving in the positive direction. Okay, so just a reminder, good review time, the sign of velocity tells direction of motion. And then G, which line segment shows constant acceleration? Well, what are we going to be looking for? On a force graph, where do we want constant acceleration? Where you have constant force. So when do we have constant force? Well, in our picture, when do we have an unchanging force? C. And so that one is C only. Everybody good with some concepts? I got one. When is the object traveling at a constant velocity? Is it C as well? Can you have constant acceleration and constant velocity at the same time? No. Okay, so maybe next time they ask about constant velocity, what would your answer be there? None. Nowhere on this one, right? Nowhere. What would you see? What would you have to see if you had if you had constant velocity? Zero force. And I guess one could argue that for a microsecond at 2 and 7, you have no force, no acceleration, right? But it's micro, right? Okay, let's do some math. Number C, letter C says, what was the velocity at 5 seconds? And so that kind of happens midway in C. And so we're looking for the velocity. I don't have a constant force. We said area gave us a change in momentum. Let's do area. Well, what did we notice about area A and area B? They're equal, symmetry. And so because of that, I know the velocity at 4 seconds returns to 0. And so if you know the beginning of that segment, then we can just find the velocity at 5. And so I need the area from 4 to 5 seconds. And it's a rectangle, okay, base times height, a base of 1 second times a height of -6 newtons. We will get an impulse of -6 Newton seconds. That's not our answer. That's not a velocity. Now what do I equate that impulse to? M delta V. And it would be V5 minus V4, which we already said is 0. Mass, I told you it's 4. And so when you divide -6 by 4, we get a -3/2 or 1.5. Go back up to our story. Did we say we were moving in the negative direction when 5 seconds came along? Yeah, so sign of velocity should match that. All right, one more and then we'll do some vector type questions. Yes. Oh, you, yes. D, what was the average force over the whole 8 seconds? Let me go back to the graph here. Gosh, it sure would be nice if it didn't change so much, right? You could, and I'm going to curse again, you could do time-weighted average. You could read the force at every second, right? And you could do a time-weighted average, but who wants to do that? What's a different, and I think easier way to find your average force for the whole time? Cancel what? Area. And what does area tell us? Impulse. So here I'm going to start in our question. What if I get the total impulse from 0 to 8 and equate it to that average force for the whole thing times the total time of 8 seconds, right? We're looking for that force. We know the time is 8, so now we just need the total area. And here's where canceling can be your friend, okay? And I'm sorry, on page 4 that y'all are going to work on, it's not a symmetrical. Sorry. But if you recognize that A and B's area cancel out, and D and E cancel out, really the total area is just equal to what? C, right? And so it equals the area of 4 to 6 seconds, okay? That's still equal to the whole entire time. We'll still use 8 seconds. It's just I only, at the end of the day, need to do the base times height for 4 to 6. Okay? And so we get this segment C area, -12, and we're looking for that average force, and the whole time is 8 seconds. Now, y'all know sometimes magic of math happens. What's 12 over 8? 3/2, which is going to come out to be 1.5, and yes, it's negative. Should I draw any conclusions that our answers to C and D are the same? No. Okay, they're both 1.5, but they're for different time intervals and they're for different variables, meters per second and newtons. So magic of math, coincidence, don't read too much into the numbers being the same, okay? And doesn't it make sense that the average is negative, not positive? Go back to the graph. You spent most of your time being pulled in what direction? I was only pulled in the positive for 3 seconds, but for 5 of 8 seconds, I was pulled in the negative. So it makes sense that it's in the negative region, okay? All right, everybody feel okay dissecting a graph? Okay, before y'all do page 4, we're gonna do some vectors. Here at the bottom is a totally new question, and then 5 and 6 has some concept questions. And so, number 6, this is a different type, so let me explain this question. Your given is on the left. Initial momentum is north or up. Final momentum is west or left. What is the direction of the average force? And your answer choices are 1, 2, 3, 4, 5, 6, 7, 8 on the right. And so this is really just a vector. So I was going north, but in the end, I wasn't going north. What vertical type of vector had to act on me? What do you need to cancel north? Need to cancel north or up, however you want to say. You need a south. Well, in the beginning, I wasn't going left or right at all. But in the end, I was only going west. So I need what direction in my answer? Left or west. And so your answer is going to be a southwest vector. So what number would we assign that? 6. And so 6 would be your southwest vector needed for you to only be going west at the end. Now, if it's not processing to you, let's do vector tip to tail method. Y'all remember vector addition? And so we're going to start out with that initial momentum direction. Now, we didn't really do it like what I'm about to do, but what would the next vector need to be? What would our change in momentum vector need to be? Well, if we do a southwest change in momentum, then start to finish would be your final, okay? Which is what they have. So it's a little different way of approaching this vector addition, okay? All right, so before y'all try number 6, or I'm sorry, page 4. I actually want to go do page 5. Got some more vector practice and conservation of momentum. By the way, I should have done earlier that baseball problem we did. What type of collision was that? When you hit a baseball. Go back to our table maybe. When you hit a baseball, what kind of collision would that be considered? Which one? Partially inelastic would be that it did bounce off, but there was contact friction force more than likely. There was deformation. We talked about the ball smushing, right? And so that hitting the baseball would be a partial inelastic. On page 5, this top one, what kind of collision is this? And I know it's not a word problem, so let's evaluate the pictures. Before, I start out with a mass of 3m. There's no velocity vectors given, so we can assume the initial velocity is 0. And then after the anti-collision, I got 2 pieces, or 3 total pieces, but 2 have given velocities. Now we'll be asked what direction. What kind of collision is this? Is that anti-collision, or this is your explosion, right? Maybe it's a literal explosion. And so for that third piece, what is the direction that it's going to go? And is it going to move faster, slower, or same? And so kind of think about that. Well, I have what I have. What do I need? And you got to think momentum is conserved here. And so you start out with no momentum, nothing up or down, nothing left or right. At the end, M1 goes north. Well, M2 is not going to do anything to that north. It's got its own right or east. And so M3, for the whole momentum to balance 0, what does M3 need to cancel north? It needs a south. And what does it need to cancel east? West. Okay. And so, hold on. DECA is canceled, y'all. She emailed back, DECA is canceled. This evening has been canceled, no longer need to leave. So there's your answer, sorry. Yeah, everything's canceled this afternoon. When school's out, go home, be safe. Good?
Yeah, exactly.
Well, I know after 4:30, it's still going to be in the 30s. Yeah. They cancel all afternoon events if it's starting in the evening. You can't just say we're canceling the 7 o'clock events, da, da, da. Better safe than sorry. Go home, get your milk and bread, right? Okay. And so what direction will M3 go? Southwest. So southwest would be the direction of M3. Is it going to be moving faster, slower, or same?
Same.
Not same. What? They're all equal mass, Miss Earhart. Shouldn't it be all the same? Why is it faster? It's the hypotenuse. So watch. Vectors. M3 needs a south. It needs a west. It's not going to do those 2 directions separately. It's going to do the hypotenuse. Hypotenuse. I don't know. I can't talk. It's virtual Friday, right? Okay, so it's going to be moving faster. Yes, it'll go off at an angle. Think about billiards, right? Now, it's not totally an explosion, but if you hit with the cue ball, right? But you can get angles. You can get angles. Okay, let's keep going here. I'm going to skip the next one just for time. Let's get the kids pushing off each other on skateboards. This could also be on an ice rink. Hint, hint, why ice, why skateboards? No friction, no external force on the system. So I know it wasn't mentioned earlier with our explosion, but we're going to do the conservation of momentum. And so here we've got two different sizes. We've got a small person and a twice as massive person. If the small person has a final velocity of v, what is the velocity of the larger person? And so I'm going to use, yes, you can do concepts. I'm going to use that conservation approach so we start getting practice with it. M small, V initial small. Y'all remember the conservation? We used impulse, equal and opposite impulse, moved it around and said that the momentum that the system starts with is the momentum that the system ends with. Now this one is going to be similar to the explosion from before. Hold on, let me focus on my subscripts. It doesn't tell us, but if these two people are on skateboards here, they're going to push off of each other. That's the norm. They're going to push off. So initially, we weren't given any velocities. What's their initial velocity before the push? What's the only number everybody can make up? 0. So it's going to be 0 on the left completely. And so what does that mean? Well, small mass is m, small velocity final is v, plus 2m, and then vf is our question mark. Oh, wait, we got to take into account direction, right? Well, we can solve for vf and get that. So what's going to happen to solve for vf? I can subtract mv. And at this point, what do you notice happens? M's cancel. And to solve for final velocity of the large, we would get a negative 1/2 v. Twice the mass, half the velocity, right? They have to have equal and opposite impulse, equal and opposite change in momentum, yes? So you could have taken an impulse approach, but we had done that a lot, so I wanted to do a conservation approach. Everybody good? Okay, compare the force on each. Already, and compare the impulse. I kind of gave it away. Compare your impulse on each. They have different masses, different velocities, but they're going to push off from each other. Compare the force of the push off on each other. Newton's third law says, if I push on you, you push on me, how much? Equal and opposite. So the magnitude would be equal. And if it happens in the same amount of time, we're touching hands, pushing off the same amount of time, compare the impulse on each. Equal, okay? Now slow down. Compare the kinetic energy of each. Now initially it's all 0. That's boring. What's the kinetic energy final? Now just play the game with me, y'all. I know it's 1/2 mv squared, but I'm not going to write the 1/2. Okay? Because 1/2 is going to be the same for each. Okay? And so I'm using not equal, I'm saying it's proportional. And so if my small has 1 mass and 1 v, and then your kinetic energy of the small is going to be a factor of 1, right? But what about for the large? It would be 2m, and what was its speed? Velocity? No, kinetic speed. 1/2, yeah, it was negative, but you're about to square it. What's the kinetic energy of the large? It's not just 2 times 1/2, it's 1/2 squared, which is 1/4, and so 2 times 1/4 is 0.5 or 1/2. So who has more kinetic energy after the push off? screen. It's right here. Who has more kinetic energy? Who has a bigger factor? The small, okay? The small. Okay. So we didn't make it to page 6. Next time, when do I see you next? Not Friday, Tuesday. We will do billiard ball example, and I'll give you some bell ringer time to work on page 4, all right?